reduces parasitic losses and improves overall efficiency. Now, to keep the overall engine displacement the same, meaning keeping the size of the engine at 2 liters or 2.5 liters, if we increase the stroke, we have to reduce the bore. A smaller bore improves combustion because the flame has a shorter distance to travel. However, it also leaves less room for the intake valves. Smaller valves restrict airflow, making it harder for the engine to breathe, especially at high RPM. Because of this, the pressure inside the cylinder builds too late in the power stroke. By the time peak pressure is reached, the piston has already traveled farther down the cylinder, reducing the force that can be applied to the crankshaft. As a result, less useful work is extracted from the combustion process, while more energy escapes through the exhaust as wasted heat. To solve this, the first thing Toyota did was change the intake valve angle to 41 degrees. This forced the incoming air to strike the opposite cylinder wall and roll downward in a powerful vertical vortex known as tumble flow. Unlike a conventional engine where the flame front spreads relatively smoothly across the combustion chamber, tumble flow creates intense turbulence inside the combustion chamber. This allows the mixture to burn much faster and more uniformly, allowing more of the combustion energy to push the piston instead of escaping as wasted heat. Toyota didn't stop there. Conventional engines use thick steel valve seat inserts pressed into the cylinder head, which slightly obstruct the airflow as it passes through the intake port. Toyota replaced these with laser-clad valve seats, applying an ultra-thin layer of wear-resistant material directly onto the aluminum cylinder head. This creates a smoother transition into the combustion chamber and increases the effective flow area around the valves. The result is improved airflow and approximately 15% stronger tumble flow, further accelerating combustion and improving thermal efficiency.
Traditionally, gasoline engines use one of two fuel injection systems, port fuel injection or direct injection. Each has its own strengths and weaknesses. So Toyota did exactly what you might be thinking. They used both. The D4S dual injection system combines port injection and direct injection in a single engine. During low-load driving, it primarily uses port injection for better fuel-air mixing, cleaner intake valves, and lower emissions. Under high-load conditions, it switches to direct injection, where its charge cooling effect suppresses knock and allows the engine to take full advantage of its exceptionally high compression ratio. By combining both systems, Toyota takes advantage of the strengths of each while minimizing their individual drawbacks.
Now Toyota was left with one thing to improve: the Atkinson cycle. In a normal 4-stroke engine, the intake valve closes near the bottom of the intake stroke. This traps the maximum amount of air inside the cylinder before compression begins. The engine then compresses, burns, and expands that air-fuel mixture. However, when the piston reaches the very bottom of its stroke, there is still massive pressure and heat left inside the cylinder. The exhaust valve opens, and that high-pressure energy is wasted. This is because the expansion stroke and compression stroke are of the same practical length. But in the Atkinson cycle, the expansion stroke is bigger than the compression stroke. Imagine a cylinder where the piston travels a physical distance of 10 centimeters from the very top to the very bottom. In a standard Otto cycle engine, both compression and expansion happen across that same 10-centimeter distance. In the Atkinson cycle, instead of closing the intake valve immediately after the intake stroke, the intake valve remains open for some time while the piston moves upwards in the compression stroke, assuming that the intake valve remains open for the first 3 centimeters on the upward movement. Because the valves are open, the air is not being trapped or compressed, it is just being pushed back out into the intake manifold. The intake valves finally slam shut when the piston has 7 centimeters left to go. Because less air remains trapped inside the cylinder, the engine performs less compression work. However, once combustion occurs, the expanding gases still push the piston through the engine's full expansion stroke, which is 10 centimeters. This effectively creates a smaller compression ratio while maintaining a much larger expansion ratio, improving thermal efficiency. This allows the engine to extract more useful work from the expanding combustion gases before they leave through the exhaust. The downside is obvious. Since less air is trapped inside the cylinder, less fuel can also be burned. That means lower torque and lower power output. To solve this, Toyota uses VVT-IE. Unlike traditional hydraulic systems that rely on slow oil pressure, VVT-IE uses an ultra-fast electric actuator to continuously adjust exactly when the intake valve closes. During light load driving, the intake valve stays open longer, allowing the engine to operate in an Atkinson-like cycle for maximum efficiency. But when the driver demands more power, VVT-IE closes the intake valve earlier, trapping more air inside the cylinder and shifting the engine towards a more auto-like cycle with higher torque. The Atkinson cycle offers another important advantage. It also helps reduce pumping losses during light load driving. In a conventional gasoline engine, when you're simply cruising or driving at low speeds, the engine doesn't need much power. To reduce power, the throttle plate partially closes, restricting the amount of air entering the engine. As the piston moves downward during the intake stroke, it has to work against this restriction to draw air into the cylinder, wasting some of the engine's own energy. The Atkinson cycle helps reduce pumping losses. Because the engine will later reject excess air, it can keep its main throttle valve wide open during the intake stroke, allowing the engine to breathe fully without restriction, eliminating the typical manifold vacuum, so the piston moves down with almost zero resistance. Then, at the beginning of the compression stroke, the open intake valve allows the piston to gently blow the unneeded excess air back into the intake manifold, drastically saving energy and improving fuel efficiency.
So that's how Toyota transformed a conventional gasoline engine into one of the most efficient production engines ever built. Not through one revolutionary invention, but through dozens of carefully engineered improvements, each recovering a little more of the energy that would otherwise be wasted. I hope you enjoyed the video and learned something new. Feel free to share your thoughts in the comments, and I'll see you in the next one. Thanks for watching.